Thank you everyone for joining us for this session. My name is Aya Takase. I am the Director of X-ray Imaging at Rigaku. In the next 30 minutes or so, I will talk about non-destructive 3D imaging study of tablets and coatings. If you have any questions, please submit them using the Q&A tool. My colleague Angela is with me and she will help you with the questions as we go, and I'll do the same at the end of the presentation. And you can download the slides of this presentation and some other resources from the Details tab you should see under this presentation view. Okay, so the X-ray technology we discuss here is X-ray computed tomography. Now, before I start, let me ask you a question. So how many of you have used X-ray CT before? Maybe to look at tablets. I'm going to give you a few seconds. Okay. So I guess some of you have done this before, maybe not too many, but that's okay. So it looks like 20% of people in the audience have done this before and 80% have not. Well, if you have done this before, that's great. And if you have not and you have no idea what it is or how it works, that's okay too. Because in this session, you will learn how X-ray CT works and how this technique has advanced in recent years. And most importantly, you will see how it's applied to pharmaceuticals. So let's start with this question. Why X-ray imaging? When you think about the formulation process, there are many steps you go through. And towards the end of this process, when you go to compression, coating, or maybe even packaging, that's where X-ray CT or imaging can become handy. So for example, if there are some cracks or capping going on in your tablet, as you see here, you can literally see it using X-ray CT. If the coating is delaminating, as you can see at this corner, you can see that too. And maybe the package is broken and something is happening inside of the package, then you might see some degradation of the tablets. Now, those are all cross-sections of tablets. And X-ray CT is a non-destructive imaging, so you can see those cross-sections without physically sectioning the tablets. But how does that work? So when you do X-ray imaging, you would put the object that you want to look at. I'm going to just use a human head as an example, and I put the detector behind it, then put an X-ray beam through the object and to the detector. Then you see what you get on the detector. And this is a 2D projection of the object. Now, X-ray CT can give you three-dimensional distribution of density. So how do we go from 2D to 3D? So to do that, you put the object between the X-ray source and the detector, then you rotate both of them together to collect the multiple 2D projections from different angles. And you put those multiple 2D projections into a reconstruction program, which reconstructs the 3D distribution of the density. And at this point, you can look at whatever cross sections, or you can make 3D rendering of different parts of your sample too. So in a nutshell, this is how it works. Now, this is an imaging technique, so you might be wondering, what's the resolution? So some of you might be more familiar with a medical CT scanner like this one. And this one has about a millimeter scale resolution. And that is not enough if you want to look at cracks or delamination on tablets. So you would use something more like this. This is a Rigaku Nano 3DX CT scanner, and this particular model can go down to submicron resolution. So inside of this machine, you have something like this. This is the incoming X-ray beam that hits the sample. Then behind the sample, you have a scintillator, which converts the X-ray image into visible light so that the light can be magnified using a regular optical lens before it hits this detector. So this particular geometry is called the parallel beam geometry, and this is very suitable when you want to achieve a 1 micron or even better resolution. Now, using something like this, you get a CT scan, and it is nice that you can see those cracks and the delamination or degradation in your samples, but you might want to quantify some of the things you're seeing. How do we go about doing that? How do we analyze CT data? Well, when you have a CT scan, something like this is a 3D rendered view of a multivitamin tablet. You see different gray levels, and it looks like a 3D volume. But what this is just a collection of 2D slices. And those slices are usually saved in TIFF format. So sometimes people call this a TIFF stack. But that's what a CT scan is. It's a collection of 2D slices. And to do quantitative analysis, you would look at one slice at a time, like this one. So this is a cross section, and you see different gray levels coming from different phases. And you can categorize them as phase 1. This one is kind of light. That means it's high density. And this is phase 2, lower density, phase 3, somewhere in the middle, so on and so on. And in this manner, you will label all those pixels or voxels to segment this image like this. And this segmentation of the original image is the very first step you always take if you're going to quantify something with CT scan. Now, this is just a 2D cross section, but you, of course, do this in 3D like this. And at this point, you can calculate the volume percentage of each phase. And you might be interested in analyzing something like surface area of small particles. So in this view, one phase was selected, and the surface area distribution is shown in the histogram. You can see that most of them are small, and purple in this case, but you see green or red particles with a larger surface area here and there, and you know there are locations too. Or you might want to know grain size of a different phase, and you can do it in the same way too. So this is how you go about analyzing CT data. So now we know how it works, how you can get the data, and how you can analyze the results. Now let's talk about what's new. So the CT technique itself has been around for a long time. The very first commercial CT scanner was invented in early 70s by Cormack and Hounsfield, and they actually won Nobel Prize in 1979. Since then, the CT scanners were used a lot in medical field. Those two people actually invented the CT scanner, commercially available ones, to look at human brains for good reason, so that you can look at people's brains without chopping up their heads. But decades later, X-ray generators got better and detectors got better. So now we can achieve a lot of higher resolution. And on top of that, computers got faster. And fast forward to 2000 or 2020, now we have things like computer vision or deep learning based image segmentation techniques. As you can see in those examples on the slide, deep learning can be used to segment very complicated images. And we can use this as just a tool to apply to CT images to do segmentation analysis. And I think this has been a game changer. You might wonder, what's the big deal about this? Well, let me show you by using an example. So this is a CT scan of a tiny particle, about a 0.5 millimeter diameter particle we took out of an orally disintegrating tablet. And inside of this particle, you see multiple phases, different coatings and cracks and different kinds of things. Let's say that we want to quantify some of those things. Then we have to do the segmentation analysis. So this is a cross section of the original image. And traditionally, you would just threshold the gray levels to segment this image. And if you do that, this is pretty much the best you can get. And this is not a great segmentation analysis, because you see those purple bits in the green phase, and those are coming from the noise. And also this core phase in this outer phase, those are two different things, but you can't tell the difference because their gray levels are almost the same. You could use machine learning. I'm talking about something simple like a random forest. Then you can clean up the noise, but still this core phase and outer phase look the same because even machine learning is based on local kind of average grade level. Now, if you use deep learning, you can take things like the shape, size, and location of each phase into consideration to do more sophisticated segmentation. And as a result, you can get something like this. Now you have no problem separating the core phase and this outer phase. And not only that, I'm going to zoom in a little bit. You can even see this very thin light gray layer as a separate phase. As you can see in this example, deep learning enabled us to do a lot of complicated or challenging segmentations, which were not possible, I'm going to say, about 5 years ago. So this has been a game changer. Now, to summarize, in the last, I'm going to say 10 years or so, high resolution CT imaging became available and deep learning based segmentation became available. So you can just do a scan in the segmentation and go on to analyze things like the porosity or pore distribution or even coating thickness distribution analysis. Okay, so let's take a look at a few tablets. I want to show you this one first just to give you perspective. So this is a tablet of about a 10 millimeter in diameter. And to look at the entire tablet, you would use 10 millimeter field of view to scan the whole thing. Now you have about 3 to 5 micron resolution. And inside of this tablet, you see those little particles with different coatings or layers. And if you want to look at those individual particles with higher resolution, you would change the field of view to match the area you want to look at, in this case 0.7 millimeter, and do a scan. And you can achieve in this case about 200 to 300 nanometer resolution to see the multiple coatings and cracks and everything inside. So the takeaway of this slide is that you can change the field of view to look at the area you want to study, and also you can change the field of view to change the resolution at the same time. Okay, let's take a look at this one. So this is an aspirin tablet. This is aspirin, and this is a hydrochalcite. And right off the bat, you can see that the hydrochalcite layer thickness is kind of uneven. You can also zoom into the surface area to see about a 50 micron thick coating, which is delaminating a little bit at the corner, and the gap is about 90 microns. And those are the things really easy to see just doing a simple CT scan. This one is a famotidine tablet. Let's call it a tablet A. This one is a very clean tablet. I don't see any cracks or aggregates. This one, another famotidine tablet, B, has actually a huge crack in the middle of it. And if you look at it closely, you see kind of dark, large areas, and those are probably on aggregates or some non-uniformity in the mixing process. Tablet C, I don't know what happened to this tablet. Something bad happened to it. This one has a huge light gray area, indicating that some sort of phase change happened in this tablet. And also those black speckles you see in the same area are indicating that there are voids. Whatever was there is gone now. And you can see, again, those different things happening, cracks or aggregates or phase change, because different materials often have different densities and they show up at different gray levels in X-ray CT. Okay, let's think about different scenarios next. Let's say that you're trying out different compression methods and wondering which one works the best. Well, you can try different methods and see what you get using X-ray CT. For example, this is a CT scan of a tablet that was prepared by rolling compaction. And the yellow one is the entire tablet. And those red areas are highlighted cracks. And you see clear two kind of planes or plates indicating that the top and the bottom parts of this tablet are capping. You can also do a high resolution scan to see, in this case, acetaminophen and cellulose mixture, and segment those two phases and see how well they're mixed. Now, that's for rolling compaction, and you can do exactly the same analysis for wet grinding and direct compaction, for example. And you actually see quite a bit of a difference, especially in the area where it's cracking. We didn't expect to see good results with no cracking from direct compaction. Those tablets were made by a group at Natoli. They made those tablets for us to take a look at. And this actually is a little bit different from what we expected, so we're still scratching our heads to interpret it. But nonetheless, the point is you can do a CT scan to see those clear differences among different compaction methods. The next example I want to show you is about crystallization. So when you're trying to use amorphous API, you don't want to see or have any crystalline materials inside of your tablet. But if they are there, it might help to see where they are and how much of it you have. So in this example, we scanned 3 different tablets with a different amount of crystalline materials. Those yellow speckles you see in the middle, you see more of them in this tablet. Those are coming from the crystalline API. And you can see them this way because there was density difference about 8% between the crystalline API and the amorphous API with a polymer mix. So that is enough density difference for us to see the crystallites. When you see them, you can segment them as highlighted red in those cross sections, then go on to quantify them. Now, using X-ray CT, not only that you can quantify how much crystalline API you have in tablets, you also know where they are and how their grains look. For example, you can tell the difference between crystallization happening, let's say, on the surface of the tablet where it's exposed to humidity, or crystallization starting from seed crystals that already existed in the original tablet. You can, for example, tell the difference between those two. Okay. The next example I want to show you is about dissolution. So let's say that the tablet you made is showing a little bit slow dissolution, slower than you hoped for. And what's causing this slow dissolution? Let's see if X-ray CT can give you insight. So those are dissolution curves. This is time and the percentage of drug released of generic versions of Lipitor. This golden curve or golden standard is coming from Lipitors, and that's the dissolution curve everybody is shooting for. And most of the generic versions tested in this study showed a very similar dissolution curve to that of Lipitor. Now, to pass as a generic version, you have to reach 80% dissolution or percentage released within 15 minutes. And in that sense, all of the curves are passing that test, but this one of the generic versions, is barely passing that test. This one is clearly slower than the other generic versions of Lipitor. So let's take a look at both of them, Lipitor in this generic version, and see what's causing this. So first, Lipitor. This is the CT scan of the Lipitor tablet, and this looks very clean to me. I don't see any cracks or aggregates, and everything seems to be mixed very uniformly. But if you do the same experiment on this generic version, this is what you get. So you see a lot of large areas that are either dark or light. The dark areas are pointed with the yellow arrows. And this tiny dot at the corner, this is a 100 micron scale bar. So you can see that those dark gray areas are millimeter size aggregates. Okay, so now no wonder why this tablet is so slow to dissolve. And this is something you can easily see when you do X-ray CT scan. But if you grind those tablets to figure out what's going on, you might miss something like this. So this is an example of a dissolution curve study. The next one I want to show you is about rapid release formula of painkillers. This is over-the-counter painkillers. I sold those 2 different pain medication at a store a while ago. This one is premium brand, and it was about $10 per box or package. And this one is a store brand, and this one is half the price. but both of them had this rapid release thing on the label. And both of them said this rapid release is something to do with this, tablet. Somewhere in the middle, there is a trick that releases the drug very fast. So I got curious and wondered where this price difference is coming from. So I did a CT scan on those tablets. So let's take a look at the premium brand first. In the middle, you see something going on there. And if you look at the cross section, it becomes very clear. So this tablet has this coating, which is probably protecting the active ingredients in the tablet. But it also has those openings of the coating. And those openings are exposing the active ingredients to the surface. So I guess the drug gets released very rapidly when you take this. So this makes sense. Now, if you do the same scan on this store brand and look at this middle section, you realize that it has the coating, but there is no opening. So I'm not sure if this really works as a rapid release. Let's take a look at both of them from the side. So the premium brand, again, it has this coating and there is a clear opening of the coating. The store brand has the coating everywhere. I don't see any opening whatsoever, but it has those kind of sleeves on top of the tablet, which is making it look like there is an opening, but there is really no opening. So this is another type of difference you can easily see. Now, I got more curious after looking at those scans and wondered, can we see what happens in the water when you put this tablet in the water? So I did a time-resolved experiment for 44 minutes using this premium brand tablet. So we did the scan for the entire tablet, but we're gonna just monitor this rapid release cross-section and another part, fully coated part cross-section. And you're looking at the dry state right now. This is a plastic container, and we're gonna put water in this space. Okay. Now, 4 minutes later, the rapid release part released the ingredients inside of the tablet very fast. And within 4 minutes, I don't see the coating anymore there. The fully coated one still has the coating almost intact. Now, we keep monitoring this for 8, 12, 16, 32, and in 44 minutes, now the fully coated part starts to dissolve. But you can clearly see the speed of releasing ingredients between the rapid release section and the fully coated section. So this is one of the time-resolved measurements you can do. Okay. The last one I want to show you is this scenario where the package breaks and something bad happens to the tablets inside. So we monitored what happens to this particular tablet in 2 weeks. And this is the one we used. The density is color-coded. And you can see the green part, that's the rapid dissolving matrix. And this yellow part is the slow dissolving shell, which is protecting the core API. At the beginning of the experiment, everything looked fine. Now, to simulate the scenario or the situation where the package is broken and those tablets are left in a really bad condition, something like 60 degrees and 70% humidity, which is actually not too far from what we have in Texas in summer. But 2 weeks later, we just left it there for 2 weeks, and this is what the same tablet looked like. You see a lot of degradation going on, and all those black parts are gone. That's void. And even the core API that was surrounded by the slow dissolving matrix is gone. We did this experiment for before and after, just 2 scans, but you can do this, let's say, every day to see gradually how this happens over a 2 weeks period. This is another type of time-resolved experiments you can do. Okay, so you saw a lot of cases where something is not right, something's not working right, or something goes wrong with your tablets. There are many things you can do just by looking at them. And what I want to suggest at the end of this presentation is to look at the tablets before you start grinding them and moving on to different analysis techniques, because just looking at them before you grind them can give you insight that might save you a lot of time in troubleshooting. Okay, so you just learned how X-ray CT works and how this technique advanced in recent years and how it can be applied to pharmaceuticals.